So I'm back. So we are going to continue with the lesson. As I was saying, we have two kinds of digital systems. The first one is the combinational systems, and the second one is the sequential system. And we are going to study them in the topics 6 and 7 respectively. In the combinational system, the output only depends on the value of the input at the time t. For example, if we want to know the output at the time t, we are going to look at the input at the time t. So the output doesn't really depend on the time. So we can remove the time variable. The output only depends on the input. This is the simplest case. Imagine that we have, for example, three switches. For example, if we activate the switch, we don't activate this switch, and we activate this third switch, a bulb is going to turn off. So this light only depends on the combination of the switches. For this light, we are going to consider that the first switch has to be 1, the second is going to be 0, and the third is going to be 1. When we have this combination in the input, we are going to have that the output is going to be 1, and the output is going to be considered as a light that is going to turn on. This is a really simple example, but you can more or less imagine as this combinational system works. In a sequential system, the output doesn't only depend on the input, but it also depends on the time. On the time means that it depends on the state, on the current state of the system. For example, imagine that we are going to use an elevator. These are the gates, and we have the button to call the elevator. When we pass the button to call the elevator, the elevator is going to do different things depending on the current state of the elevator, of the system. If we press this button and the elevator is in the same floor as us, the gates are going to open. But imagine that we press this button and the elevator is in another floor. So the state is different. In this case, what is going to happen is that the elevator is going to close the doors, go downwards to our floor, and open the doors again. So the input is going to be one thing that the system has into account, but the system is going to has into account also the current state of the system. The state is represented by this function, and this is going to be the output. So the output of the system depends on the input. We press the button to call the elevator and the current state of the system, if the elevator is at our floor or is in another floor, etc. So we have into account the input and the state function. We have we have several functions here that we are going to see in more detail in topic 7. So more things about digital system. Well, you already know more or less this. The logical design consists in creating digital circuits that implement digital functions using logic gates. The logic design is what we have done in the final part of logic 3. We have designed, for example, NAND or NOR logic gates. The logic gate using transistors. A logic gate is an electronic circuit that performs an operation. Do you know this from topic 3? If we connect several logic gates to have a more complex function, we have a logic design. Okay, you have to know this. In logic design, we connect logic gates to implement a function. Logic gates are commercially available. You can buy in shops, in any electronic shop. For example, near Carrefour Alameda, here near the faculty, we have several electronics shops, Electrónica del Futuro, Electrónica 90, and you can buy in these places logic gates. This is a logic gate, a real logic gate. Okay, normally inside the chip we have several logic gates, not only one. So the mathematical framework, the mathematical theory that we used in logic design is called switching theory. Okay, and the mathematical foundation is switching algebra or Boolean algebra. So we are going to study a specific type of algebra that is going to be really useful for logic design. The the biggest difference when comparing the Boolean algebra to another kind of algebras is that in this algebra numbers and variables are going to be always zeros and ones. So we are going to see more things about digital system. The first things we are going to study is the numeral system. I think that we can go here more or less fast because you are familiar with this, because you are used to work with a numeral systems from the childhood. The numeral system based on with base 10, the decimal numeral system. Here we have some definition that we can understand better with examples. The elements of an alphabet A can be represented using symbols of another set, considering that the B set is the cardinal of the B set. The cardinal is the number of elements, is much smaller than the cardinal of the set A, that is the alphabet. It may seem confused, but it's really simple. We are going to consider, for example, that the A alphabet is going to be numbers between 0 and 99. So this set, this alphabet, is going to be 0, 1, 2, until 99, 98, and 99. So this is the alphabet A, and it has 100 elements from 0 to 99. So we can represent these elements using a set of symbols that we are going to name B. And the set B is going to be these symbols: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So the cardinal of B, the number of elements, is 10, and we have that 10 is much smaller than 100. So we can use the element of B to represent the element of the alphabet A. So we are going to do this. 0 is going to be this element of B. 1 is going to be this element. 2 is going to be this element. So we can reach 99. So you can check that we can represent the element of the alphabet A with combination of symbols of the set B. So every combination of symbols of B is called a word. Okay, we are going to use this definition often. Every element of B is going to be called digit. And you are familiar with this, you know what a digit is. What is the base? The base is the cardinal of B. So here base is 10, is decimal base. That is the base that we use normally in our daily lives. The highest digit of b is going to be the cardinal of b minus 1. That is 9. That you can check, that is the highest digit. I think that it is, really easy to understand. And we can apply this to another kind of alphabets and other kinds of sets with the different symbols. So we continue. Sorry, this is not the software. We are here. Okay. So the numerical representation in base B. So we are going to encode the alphabet A using the symbol of B and forming words. And that is exactly what we have done here. This is the element 0 is codified using these two symbols, and this is a word. Okay? It's really easy to understand. The numerical value is fast to obtain doing this mathematical expression, and I'm going to put an example here. For example, we have here this element. This is a word, okay? The word that has these three symbols, and we are going to consider the position of each symbol, 0, 1, and 2. So we are going to multiply each symbol by the base raised to the position, and we are going to sum the symbols. The position 1, the position 2, and the first position that we are going to consider, the position 0. So this is 9, this is going to be 20, and this is going to be 100. If we do the sum, we have the number 129. I think that you have studied this in high school, but I have to repeat it, but it's really simple. More things about this kind of numeral systems. Here we have some properties that we have already seen. Each representation is unique. For example, for the number, for the element of the alphabet A, 80, we have only this symbol. This symbol is not does not represent 80. These symbols does not represent 80. We only have one combination of symbols that represents an element of the alphabet. Every element of B is called digit. The number of elements is called the base of the system. In the decimal base is 10. The highest digit is 10 minus 1 is 9 in the decimal base. This may change when using different bases. Each element of the alphabet is called a word. Okay, this is a word, 0, and this combination. The number of words in an alphabet is given by the base raised to the number of digits, and we can see this clearly here. The base raised to 2 digits, it's 100. That is the name of elements in the alphabet A. And we have 2 digits because we are using 2 digits. 1 digit and another digit. And here we have the number of digits to encode all the elements of a specific alphabet. We are going to see this when using different alphabets and different bases, but it's quite simple. N has to be equal or larger of logarithm in base 10 of the cardinal of A, that is 100 element, and this is 2. So we are using 2 digits, 2 symbols of to symbol of B to encode of the words of the alphabet. more things. Now we are going to see at different bases. We are used to use the decimal base, but we are going to see the base 2, the base 8, and the base 16. When the base is 2, we have the binary system, and the elements are 0 and 1, and the cardinal is 2. When we have a binary number, we are going to consider the bits. Okay, digits are called bits in the case of binary systems. The bit that is to the left is going to be called the most significant bit, and the bit that is to the right is going to be called the least significant bit. We have as well the octal system that has 8 elements, and the base is 8. And we have also the hexadecimal systems that has 16 elements. Note that in the hexadecimal systems, when we reach the 9, we have to add more digits. We can use 10 here because 10 is 2 digits, is the decimal base. In this base, we need more elements to reach the 16 elements. So after the 9, we use A, B, C, D, F, and they represent 10, 11, 12, 13, 14, and 15. So the elements goes from 0 to 15. Here we have examples of all these numeral systems when going from 0 to 15. We have 16 elements. We know the decimal case. What happens with the binary case? In the binary case, we have 2 elements. We have 1 and 0. When we reach the maximum, we are going to repeat the 1 and 0, but adding zeros to the first part and 1s to the second part. Now we are going to repeat these 4 combinations, but adding a new 0 to the first part, 1s and 1s to the second part. So following this reasoning, we can build any number in binary. Now we are going to repeat all the previous combinations, but adding zeros to the previous part and 1s to the following part. So using the reasoning, you can make, as I said, every number. In the octal numeral system, when we reach the maximum, we repeat the same sequence, okay? But adding zeros to the previous part and 1s to the second part. And this works for any base that don't have enough elements to reach all the work of the system. In the hexadecimal numeral system, we don't need extra elements because this system have exactly 16 elements that can be used to codify an alphabet of 16 elements. Okay, I'm going fast because I don't have to answer questions, but write down your question. Okay, we are going to see now conversions between numeral bases. We are going to go from any base to decimal, okay? So from binary, from hexadecimal, from octal to decimal. We are going to use these 2 examples. In fact, the formula is the one that I previously used. So I'm going to delete all this. So, for example, I'm going to convert this number from base 2 to decimal. So the position is 0, 1, 2, 3, and 4. So we are going to do the following. The most significant bit, the first bit in the right, is multiplied by the base, that is going to be 2, rise to the position plus the following bit multiplied by the base rise to the position this is 0, this is 2, this is 4, this is 0, and this is 16. So if we sum all the values, we have that the decimal number is 22. Okay, if we use, for example, a number in the hexadecimal base, we have the following: position 1 and 2. Okay, so it's 8 multiplied by the base rise to the position A is 10. I told you that A is 10. You can look at the table. Okay, here it's clear. A is 10. Okay, and F is 15. Yes, F is 15. So this number, if you do the calculation, is this one. You have a useful tool in Windows that is the calculator. If you open the calculator of Windows, you can select the mode programmer, programador in Spanish, programmer in English, and you can do here the conversion. For example, I'm going to introduce this number in hexadecimal, that is HAF, and you can see the value in the base decimal, in the decimal base, the value in octal, and the value in binary. So using the Windows calculator in programmer, you can check the base conversion and if your exercise is right or not. Okay, so now we are going to see how to convert, it's here, how to convert from the decimal base to any other base. We have to use the method of the successive divisions. I'm going to show you how these methods work. So for example, we are going to consider that we can convert from 13 in binary to decimal. 13 in decimal to binary. So the method of the successive divisions is the following. We are going to divide 13 by the base. The base is 2. So if you remember the division that you made in high school or in primary school, this is the quotient is 1. Sorry, the quotient is 6. 6 is 6 multiplied by 2 is 12, so the remainder is 1. Now we are going to continue with the divisions. This is the remainder. We continue with the division using the base. This is the remainder. Here we have, we have already finished. So how we are going to construct the binary number? We are going to go from the quotient, and we are going to take the remainders in these directions. So our binary number is going to be 1, 1, 0, 1. Okay? That is 1, 1, 0, 1. And you can check it in the calculator of Windows. 13 in the decimal base